Good morning all, this is Dr. D. Khalandar Basha, working as Associate Professor in Institute of Aeronautical Engineering, Dundigal, Hyderabad. Today we are going to discuss questions from Module 4, which is System Design using Microcontroller, under the course Microprocessor and Microcontrollers. So first we will see the first question. Demonstrate the program to make the stepper motor to rotate clockwise direction in 8051 microcontroller. So for a stepper motor, it is going to have 4 windings. What we will take as winding A, winding B, winding C and winding D. So these 4 excitations, when we give the pulse, in what way we are exciting, what is the order we are following, depending upon that, the stepper motor can be rotated in clockwise or anti-clockwise. Suppose if you are given the pulse first for winding A, then for winding B, winding C, winding D, from there again winding A. So then the stepper motor will rotate in clockwise rotation. If the windings are excited, first winding A, winding D, winding C, winding B, then winding A, then the stepper motor will rotate in anti-clockwise rotation. So the rotation of the stepper motor will depends upon how we are going to give excitation. The possibility of excitation we can give at a point, either we are exciting only one winding or 2 windings. There is a mechanism for rotating the stepper motor in clockwise or anti-clockwise. Here this is the case where we are going to excite only one winding at a time, but we can also go for exciting 2 windings at a time. Let us consider, I will take the first clock pulse for exciting winding A, winding B. In the next clock pulse, winding B, winding C. In the next one, winding C, winding D. After that, winding D, winding E. So then the stepper motor will go in the clockwise rotation. This is 2 windings exciting at the same time. For anti-clockwise, winding A, winding B. The next clock pulse will be given for winding D, winding A. Next one will give for winding C and winding D excitation, followed by winding B, winding C excitation, then winding A. So then the stepper motor will rotate in anti-clockwise rotation. So these are the excitation we can give for clockwise as well as for anti-clockwise. So as per problem statement, we want to rotate in clockwise rotation. So we will write the program for rotating the stepper motor in only clockwise rotation. So for clockwise rotation, so what is the pulse I can give? The winding A, winding B for excitation, the pulse we are going to give as 1100, which is C. The pattern we can write as C. 0110, which is 6, 0011. In the hexadecimal I am writing 3, 1001, which is. So for exciting for the first time, which windings we have to take? Winding A, winding B, winding B, winding C, or winding C, winding D, or winding D, winding A. So any one of this pattern we can do. So after 4 clock pulses, for getting the same pattern, so we are going to write the value will be repeated for 2 times, that is upper nipple and lower nipple, so that whenever you go for rotating the next pattern to generate. Now if you observe, see here, the pattern, if you shift towards the right side by 1 bit, we are going to get the next patterns. What about this? This I want to get here. But as the data is 8-bit size, so this will move to MSB. So if you trace back, you can see the pattern which we can send here. It is either CC or 66 or 33 or 99 each. So the pattern which we want to load, that will be moved into accumulator. What are the possible combinations I can give is CC, 66, 33 or 99. So any one of this pattern we can load into accumulator. We are assuming the stepper motor is connected to the port 1 of 8051 microcontroller. So this is a stepper motor. This stepper motor is connected to the port 1 of 8051 microcontroller. So when I want to send the pulses to the stepper motor, we will make use of port 1. So now if you send some data onto the port 1, that will be driven for stepper motor. So what are the pattern which we are going to load in the accumulator? That will be moved to port 1. For getting the next pattern, we have to rotate these contents towards the right side by 1 bit. So for rotating right side, we will take rotate right instruction of the accumulator content. So this will rotate the contents of accumulator. Previously it is 66H. How we can write in the binary format? 0110, 0110. This is 66H. So for next excitation, we are going to shift this one towards right side by 1 bit. So this one will be placed here. This one, next 0, 1, 1, 0. This 0 will be placed here. So what is the pattern I'll get is 33. So for that, we will rotate the contents of accumulator towards right side by 1 bit. What are the pattern which are generated now? That we are going to be sent to port 1. Then after each and every rotation, we will call for some delay. Then we go for executing from mine to L. So this loop will be used for generating continuous number of clock pulses for exciting the windings of the stepper motor. Here we are not limiting how many clock pulses we are going to have. If you want to limit, here you can write one counter. Let us consider move R0 comma some 100 pulses. Then here instead of S jump, we go for decrement and jump on no 0. So then you can limit how many pulses or how many rotations we want to rotate the stepper motor, that we can limit. Here. So if you want to limit for some number of rotations. So here we were sending 32 steps. So this we are going to be loading to R1. Rest of the program is set loading 66 into accumulator, rotating, again sending to port 1, call. Done. As we want to limit the number of rotations, we are going to send how many clock pulses will be loaded into R1 register by using move R1 comma hash 20H, which is we are going to send 32 steps here. After each pulse is excited, then we go for decrementing R1. For decrementing R1, we will write an instruction DJNZ. DJNZ stands for decrement, and if it is non-zero, go to the label specified. So for every iteration, R1 will be decremented. If the contents of R1 is not equivalent to 0, loop 1 will be takes place. That is, control will be transferred to loop 1. So this loop will be takes place until the count which we are loading into R1 register is equivalent to 0. Once it is equivalent to 0, we will come out of the loop. Then we can terminate by using the HLT instruction. Describe the program to make the stepper motor to rotate in anti-clockwise. Only the difference from clockwise and anti-clockwise. In clockwise, winding A, after that winding B. So the pattern we are going to shift towards right side. So instead of that, if you are exciting from winding A to winding D, so for generating that, we go for left shift. When you do the right shift operation of the accumulator contents, this will generate a clockwise rotation. The same accumulator contents, if you rotate towards left side, so it is going to generate the anti-clockwise direction. So in the previous program, wherever R or A, that replace with RLA. Now the program will work for anti-clockwise. Show the circuit diagram to interface 4:1 keypad with the microcontroller and explain how microcontroller recognizes the key is pressed. So here we are going to take 4x4 keypad, where we are going to have row 0, row 1, row 2, row 3. This I will take as column 0, column 1, column 2, column 3. Here we are going to have a switch. So for every cross section of row and column, we are going to define a key. So as we are having 4 rows and 4 columns, the number of switches which we can connect or the number of key we can have in a keypad is limited to 16. So once all these switches are connected in this manner, the column value will be connected to VCC, all the column entries through some resistance. Right. Here we are going to connect this one to one of the port. So where we are going to read this particular port. If any switch is pressed, so this switch will be closed. In that case, this node will be pulled to the value which we are having on R0. So this also will be connected to another port. This I'll take as some port to 0 or this one as port 1, any port. So first we'll pass all the values as zeros in this port. So whenever any switch is closed, this point will be connected to ground. So whenever you read this column, so here it is pulled to ground. So this will be read as 0. Indicate one of the switch which is present in the column 0 will have a key which is pressed. Suppose if none of the key is pressed, it is going to written as 1. So first we will check all the columns by sending all row values as 0 initially. We will read all the columns. If all are written as 1, it indicates no key is pressed. If you will get a pattern other than 1111 for the lower 4 bits of any particular port which are connected, if it is other than 1111, then it indicates some key is pressed. So what are the key which you have pressed? Either it may be lies in column 1 or column 2 or column 3 or column 4. Later we will see how we will check that. So this is a typical diagram for 4x4 keypad interface, where port 1 we are using for row connection, port 2 we are using for column connection. At any point, if the switch is closed, let us assume I am taking the switch C6 is closed. When the switch C is closed, as we have placed the initial value for all the rows is equal to 0, this node will be pulled to 0. The rest of the columns will be connected to this. As no switch is connected, here you get as 1, 0, 1, 1. So if you read any column as 1, it indicates the switches which you are connected in that particular column are not pressed. If any column is read as 0, it indicates one of the switch is closed. Which switch is closed? Either it can be a T2 or 6 or A or. For finding out this, one row again you will send 0 and the remaining rows will keep as 1. So when you make this one as 0 and the remaining rows as 1, so what is the value it is going to read? Because it is 1, the switch even though it is connected, this will be pulled to 1. So now here you will get all the values as 1. It indicates the 0th row of the keypad, the keys are not pressed. So that means 2 is not pressed. Then we go for making D1 as 0 and D0 as 1. Now we will write this. As 6 key is pressed, here you will get this one as 0. When you get this one as 0, we can know that the switch which is having the placement in row 1 and column 1. I am taking this is row 0 and column 1. So this intersection we are going to consider as the key is pressed. Now we will see the program. To configure the port 2 into input port, we will write the port 2 as FFH. As it is starting with alphabet, prefix with 0. Clear the port 1. Next, move A, port 2, read the columns. Once we read the columns, we want to examine only the lower 4 bits, whether these 4 bits are 1, 1 or not. So for that purpose, whatever the port 2 values which you are reading, we are going to clear upper 4 bits. These values will be retained as it is. So for that, we go for ANDing with 0FH. So if any bit AND with 0 will return 0, if any bit AND with 1, it is going to result to the same bit. So for that purpose, we go for AND. So once we AND, the upper 4 bits will be cleared, the lower 4 bits will be retained the same value. If the lower 4 bits are 1, 1, 1, 1, it indicates no switch is closed. So for that, we will see here. Compare. What we are comparing? After ANDing, accumulator contents with 0, 0, 0, 0, 1, 1, 1, 1. That is 0 FH. After comparing these two, if they are not equal, go to the label key 1. So this key 1 loop will be executed if no key is pressed. This will be executed repeatedly if no key is pressed. So let us consider if any key is pressed. What happens to this comparison? It will fail. So it will come to the next. So once any key is pressed, we will call some delay. It is for debouncing. Now we are going to read the port 2. Again, we will AND with 1, 1, 1, 1. We will check whether it is key is pressed or not. So let us consider if the key is pressed. So what we will do is, we will send the row 0 as 0 and the remaining bits as 1. So this is for checking row 0 switches. Once we make the row value as 0, we are going to read the column values. Again, we will AND with 0 FH. Again, we will compare with 0 FH. If it is not equivalent to 0 or 0 F, it indicates the key which is pressed is not related to row 0. So otherwise, we go for row 0 for fetching which key is pressed. Similarly, we will check for row 1. This is for row 2. This is row 1, row 2. The next instructions for row 3. Right. So any one of this, it is going to be satisfied. Then we are going to load. Once we know that the key is pressed, either it may be row 0 or row 1, corresponding control bit takes place to that particular label. So we'll load the address of the key code value. Then we go for finding out by calling the label find. So it is for row 0, row 1. Same logic will be applied for each and every row, row 2 and row 3. In the find, what we are doing is, once we read the column values where the switch is pressed, so we are going to have, this is 0th index, 1, 2, 3. We will find out only these 4 positions. So for that purpose, we are going to rotate the accumulator contents towards right side. If JNC, that means after rotating towards rights, if carry flag is not equivalent to 0 or 1. So when any key is pressed, what is the value you are going to get? 0. So if you get any bit is equivalent to 1, it indicates no switch. If 0 indicates yes, key is pressed. So we will check JNC. If carry is equivalent to 1, match. Otherwise, go for next finding out. Right. So in the match, we will clear. We are going to fetch the ASCII value from the table by loading the address into accumulator plus DPTR, where accumulator will have the offset, DPTR will have the starting address. From there, we are going to get equivalent value that is existing in the table. Next, what are the value which you are getting? Equivalent value that will move to port G. So this will looks like a ASCII lookup table where code 0 it is for row 0, row 1, row 2, row 3. Next, explain ALP to generate triangular waveform using 8051 microcontroller. So for generating a triangular waveform, see if you observe the waveform for the triangular wave, it is keep on incrementing manner from 0, 0 to maximum value FF. Then it will go on decreasing from FF to 0, 0. So for rising, we will send the values by incrementing. For getting a negative slope, we are going to give as a decrementing manner. So in 8051, we will select some port. This port will be connected to a DAC. The DAC will generate the triangular waveform. So what this 8051 controller is going to give the input for DAC is initially 00, next 01, 02. Like this, it is going to continue until FF. Once it reaches to FF, from there it has to return from decrement manner. FE, next D, FC. So like this, it will be continued until 00. Once it is 00 rejected, then we will go for next iteration for getting continuous. Now we will see the program for it. Clear accumulator, increment accumulator for sending 1. Accumulator contents will be posted on port 2. We will compare whether the maximum value is reached or not. If it is not reached, again go to this. So here, this code will generate a triangular waveform starting from 00 to FF. Next, once this FF is generated, then this condition will be satisfied. Not satisfied, it will come to next one where we can call a small delay. Then we go for decrementing for generating a negative pulse. So here, this loop, down loop will be used generating the pulses from FF to 00. In the following program, we create a square wave of 50% duty cycle with equal portion of high and low because it is 50% duty cycle. On the port 1.5 bit, timer 0 is used to generate the timer delay. Assume the program, calculate the delay generated. Assume XTA, that is clock frequency, is equal to 11.0592 MHz. So this is the program where we need to find out what is the delay this program is going to generate. So now if you observe, here the timer 0 used, what is the count we are having is FF. This is the count which we are loaded. And this is the program for delay program. Now we need to find out what is the delay it is provided. So this is also second problem statement in the same manner. Find the delay generated by timer 0 in the following code using X as well as in the decimal method. Do not include overhead due to instruction. So now here also mode 0 is used. Timer 0 is used. The count we are going to be loaded is B83H. So for finding out what is the delay they are providing by using this program is, as it is 16-bit timer, we are going to get the maximum value is FF minus B83H will be loaded. As the count starts from 0, we are going to add +1. So it is going to give as 47C2H. In the decimal, it is equivalent to 18,370. So for 1 clock pulse, the time period is equivalent to 1.085 microseconds. Multiply this one with the number of counts it is taking place. So which is going to provide 19.93145 milliseconds. So when the count starts from B380H, every pulse it will be incremented until FF. Whenever it will overflow from FF to 000, then it indicates the time which is generated is going to be satisfied. So 18370 into 1.085 microseconds, where this one is the time of 1 clock pulse. How many clock pulses we are giving? 18,370. So which will give us 19.93155 milliseconds as the width of the pulse. As it is a 50% duty cycle, approximately 20 milliseconds in logic 0, 20 seconds in logic 1. So which is equivalent to 40 milliseconds of the pulse width we are going to get for a square wave. Demonstrate an ALP to generate sawtooth waveform using 8051 microcontroller. So earlier we have discussed for triangular wave. In the same manner, we can generate the sawtooth. The only difference is here we are going to generate the pulse from 00 to FF. Once it reaches to FF, again it will be fallbacks to 0. Again it starts from FF to 00. After once it reaches to FF, immediately it will be changes to 00. Then again it starts. So clear accumulator, increment A, send to port 2, check for maximum value. Once it reaches to maximum value, call delay, then jump on. So this will keep on executing. Once it reaches to FF, again once you increment it, then it is going to 0, 0. So it will generate a sawtooth bill. Develop the program to transfer the message IARE serial at 4800 baud rate in mode 1, that is 8-bit UART in 8051 microcontroller. The T mode value for generating given baud rate, we have to load T mode with the 20H, and TH1, as it is the auto loaded port, we have to load only TH1 is sufficient with FTH. SCON is loaded with the 50H. To start the timer, set bit TR1. First character we want to send is I, so that will be loaded into accumulator. Then we will call the function transmit the character. After returning from the subroutine, then we will move the character A into accumulator. Then again we will call. So this TX underscore CH is a subprogram, a subroutine where we wrote a function how to transmit the data. So every time we are going to load the character which you are going to be sent into accumulator, from there the data will be transmitted serially. So I, A, next one is R and E. So what we'll have in the subroutine TX underscore CH is, so whatever the accumulator content is there, that will be loaded into SPOF, because the serial communication is used for transmitting the data which is available in the SPOF register. Next, we are going to check whether the transmit interrupt is active or not. If it is not active, go to the same level, that is same instruction. So this will be keep on checking the transmit interrupt. Once the transmit interrupt is occurred, clear the transmit interrupt and go to main program. RET is the last instruction which we are going to write in the subroutine to return from a subroutine. Describe the interrupt management of 8051 microcontroller. So in 8051 microcontroller, total we have 5 different types of interrupts can be generated. 2 are related to timers, 2 are related to external interrupts, 1 serial. So 2 interrupts are set aside for hardware and external interrupts, which is on INT 0 bar and INT 1 bar. And 2 interrupts are set aside for timers, that is timer 0 and timer 1. 1 interrupt, that is single interrupt for either it is receive or transfer. So however, the reset pin of 8051 may also considered as an external interrupt source. So the function for executing the reset will have a code which is at 0000H. So that will be loaded into program counter. Now for enabling the interrupts in 8051 microcontroller, we have to configure 2 registers. One is interrupt enable register, the second one is interrupt priority register. So the format of interrupt enable register is shown in the figure, where we are going to have the LSB is EX0. Whenever you write the particular bit, so I'll write as BI. BI is equivalent to 1. It indicates the enable of the particular kind of interrupt. When that particular bit is equivalent to 0, so the interrupt which is on that particular interrupt source will be disabled. So bit 0 it is for EX0, where we want to enable the interrupts which we want to receive on INT0. For INT1, we have EX1. For timer 0, we have ET0, enable timer 0 interrupts. ET1, it is for enabling the interrupts for timer 1. ES, it is for enabling the interrupts on serial port. Either it may be transmit or interrupt. Any one of these 5 interrupts, if you want to enable, we have to write enable this EA bit is equivalent to 1. If you make EA bit is equivalent to 0, this will be considered as don't case. Even if you pass 0 or 1, no significance, because EA is 0. The next register is IP, which is interrupt priority. So whatever the interrupts which we are enabled, if you want to give the priority, the corresponding bit we have to write as 1. So where this 1 indicates, we are giving the priority for it. When you write that particular bit is equivalent to 0, so no priority you are assigning. So the priority for INT 0, priority for INT 1, priority for timer 0, priority for timer 1, priority for serial communication. This is interrupt priority register. Next, we will see describe mode 2 for serial communication in 8051 microcontroller. So, serial communication for mode 2, it is 11-bit full duplex transceiver. Out of these 11 bits, one is start bit, 9 are data bits, one is stop bits. So, the interrupt flag TI or RI will be set once transmission or reception is over. So, in this mode, the baud rate is fixed and is determined by the overflow of the timer 1. So, the baud rate is given as 2 to the power of S mod divided by 64 into oscillator frequency. Compare timer and counter, analyze 16-bit timer mode and 8-bit auto reload mode. So 16-bit timer means where we are going to use both the lower 8 bits and upper 8 bits of the registers TL0 and TH0 for timer 0, TL1 and TH1 for timer 1. Whereas R2 reload mode, it is only 8-bit timer. Once that 8-bit timer overflow is occurred from FF to 0000, then THX will be loaded into TL0. We will see diagrammatically. So it is mainly used for generating of the baud rate. So as we know, the timers we can configure in 3 modes: mode 0, mode 1, mode 2 and mode 3 also. 4 modes. Mode 0 is 13-bit mode. Mode 1 is 16-bit mode. Mode 2 is auto reload mode. Mode 3 it is for split timer, where we can use timer 0 as 2 separate 8-bit timers. So this is the logic for timer or counter. So whenever we make the timer run, then only the clock pulses will be sent for the timers. So if C by T bar is equivalent to 0, it is for timer. So the switch will be connected to the clock pulses which we are getting from oscillator. If you are using as a counter, that is C by T bar is equivalent to 1, then we are going to accept the inputs which is on T1 or T0. It is going to count. So the switch will be closed depending upon TR, gate bit and INT bit. So in mode 1, the 16-bit timer, where we are going to use the lower 8 bits of TLX, THX and THX will be used. So the maximum count which we can have here, it is 65,536 pulses we can generate. The ranges it is from 0 to 65,535. So this is for every pulse, the TLX will be incremented by 1. Once this TLX by adding 1, whenever it reaches to FF, then it will be overflow to 00. Whenever this overflow is occurred, this will make the THX will be incremented by 1. Here also, it will keep on incrementing until FF. For the next clock pulse, it will be reset from FF to 00. Once this overflow is occurred, then it is going to generate the overflow on either it may be timer 0 or timer 1, interrupt will be generated. Next one is mode 2, which is auto reload mode. In this mode, load the THX bit with the 8-bit value. When the timer gets started, the THX gets automatically loaded into the TLX. So first we are going to load the TLX value with the THX value. For every pulse, the TLX value will be incremented by 1. So this will keep on incremented until FF. Once it reaches to FF, then it will be overflows from FF to 00. In that case, it is going to generate a overflow, as well as this will make the THX will be loaded into TLX again. So that is called as auto reload mode. Continuously, once it will generate a overflow, again it will start from counting. What are the count we are loaded into THX register. So thank you. In this session, we have discussed a few questions related to Unit 4. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.